All right, good morning, everybody. Welcome to Oak Ridge National Labs. I hope you're enjoying yourselves thus far. I know that you guys have been covering a lot of different areas and a lot of different topics and such. I know that Cheaton has gone through, the theory of topological superconductivity, and I believe On Ping has actually looked at some of the surface science, really focusing a lot on like scanning, tunneling, microscopy, and spectroscopy, which is of course vital to understanding these materials. And I believe Steve and Jesse is actually going through looking at some of the nanofabrication processes of how we actually think about turning materials into devices. But with that, there is one critical aspect that we need to kind of think about and go over, and I'll try to give you a brief overview of what that is. And essentially, it is how do we actually make the materials, and then how do we control and tune the materials to kind of optimize the property of interest. And today I'm going to be talking again and focusing on these topological superconductors. So for quantum computing, so the idea why we're actually doing this, and so I'll briefly kind of go over some of these aspects. So in essence, we have qubits, of course, which have, or classical bits, which have ones and zeros. And the idea here is we want to have these quantum bits, where we have these superpositions of two different states, and these qubits can be sort of in any a superposition of these states, which makes them very information rich. And so this is the beauty of trying to think of qubits to do computational efforts, because we can take the superposition of these different states into individual qubits and then entangle a bunch of qubits together and let them evolve, and then perform a measurement to see the ones and the zeros that are encoding the actual solution to the problem that we encode into the qubits. And so it's a different way of actually doing, computations, very data intensive, and it allows us to solve a lot of problems that are very hard to solve using classical computational methods. The challenge here, though, is a lot of these qubits and a lot of these quantum states are very sensitive. In essence, quantum mechanics, it couples to the environment. And so it's very hard to kind of isolate a lot of these quantum states to give us very reliable and robust information. And so a lot of the computational efforts right now looking, for example, superconducting qubits, you can have cosmic rays and just X-rays and other, coupling to the environments that just disrupt a lot of the quantum wave functions that you're wanting to use for these calculations. And so we want to find new paradigms and new materials that kind of help sidestep and make them more robust against these decoherent bottleneck. And so this is one of the ideas of looking at topology to see if we can, enhance the robustness of these quantum wave functions and these quantum states for us to be able to use them for these quantum calculations much more robustly. And so here, there's a lot of this theoretical architecture out there that kind of can teach us how to do this. And now we want to see if we can physically realize a lot of these platforms in order for us to do, quantum computation, looking at some of these non-abelian statistics that are proposed to be supported by these topological materials. And so in essence, we want to understand, how can we make these materials? How can we tune these materials to make the devices? Because the topology is in essence a band structure effect. And so, the idea is a lot of, in theory, these can survive at much higher temperatures and will be much more robust against, interference from a lot of the environment and a lot of local disturbances that can disrupt a lot of the other quantum states that are used for other computational paradigms. So in essence, how do we get there? And I know Cheaton really went through, I'm sure, in detail about how to generate a lot of these states. And so I'll just kind of briefly overview these quickly. But in essence, the key is, in the electronic structure, you want to, log the electron spin to its momentum, rendering it, effectively spinless. And so if you have this model band structure, you can add a Rashba effect, which can split these bands. If you add a magnetic field where they overlap, they will start to interact. And so now you're left where on one side of this Fermi level here, you have a spin in one direction. On the other side, it's in another direction. And so now when you proximitize this with a superconductor, you get this possible P-wave superconductivity, which can host these Majorana modes. And these Majorana modes are the quasi-particles that can kind of have this non-abelian statistics, which is what we're after for a lot of these quantum computational efforts. And so there you can use dimensionality. So with topology, there's always this bulk boundary correspondence. And so Microsoft has done, a fabulous job of looking at these 1D nanowires where you have these Majorana modes. And a Majorana mode is sort of it's a particle that is its own antiparticle. It's sort of half a hole, half an electron. And so, we want to use these things for these efforts. And so here they can see that they have these Majorana modes that are trapped at the ends of these wires. You can also look at a lot of these chiral modes. If you have sort of a 2D system due to the bulk boundary correspondence, once again, you can have these chiral modes that'll kind of, propagate around the edges of these materials or these islands of materials. And so now you can kind of think of having kinks or defects or something inside these two-dimensional islands that can kind of trap these Majorana modes. And so now you can think of paradigms of how to control the spacing and the interaction of a lot of these different particles. But one of the things that we've really been focusing on is this Foucault model. And so here is where you take a 3D topological insulator and proximitize it with an S-wave superconductor. And so once again, with this, the topological insulator, you have these spin momentum block, boundary states. So in essence, you have these electrons that are propagating along the surface that have, the spin of the electron is locked to the motion or the momentum of that electron. And so now, once again, if you take these spin resolved states and, proximitize it, this is once again, you have this sort of spinless P plus IP superconductor, which is a platform that could host these Majorana modes. But in the end, how do we realize all these? So I've talked about all the, topology and electron and superconductivity. But in the end, this is all of the quantum players that you're looking at. So you have these structures and you have the electrons that are, hopping along these different crystalline structures, which will give you a band structure, an electronic band structure. And whether it's a metal insulator or so forth depends on where the Fermi level is and the shape of this band structure. But then you have a lot of the many-body physics that can alter the properties of this electronic structure. And so you have the electron and you have the charge, spin, orbital, and the phonons, and all of these can kind of couple together in different ways. And this many-body physics is what gives us a lot of these exotic properties. And so for classic BCS superconductors, it is, the electron coupling with phonons in the material to kind of give you a pairing glue for the superconductivity. For a lot of these topology effects, we have this orbital degree of freedom that couples with the spin, which can kind of reorder bands, and the ordering of these bands will be different inside the material than what they would be outside the material. And so this is where you get these interfacial states that have this unique spin texture as you stitch these two different types of band structures together. But in the end, all of this exotic physics is created by these very few players. But this is true regardless of the quantum materials that you're looking at. And so there is a rich array of all of these quantum materials that we want to understand and we want to be able to utilize and harness for all of these applications, beyond just topological superconductivity and quantum computation. So spintronics, valleytronics, there's a whole slew of different potential applications that we could realize if we can learn how to control these sensitive players and these interacting competing degrees of freedom. But, the interesting thing is all of these are governed by the electronic structure near the Fermi level. And so a lot of these quantum properties of interest are going to be governed by this electronic, structure at the Fermi level and all of the many-body interactions that are encoded into that electronic structure. And so here I'm going to kind of give you an overview of how we make the materials and then how we can interrogate the electronic structure of the materials and optimize it to kind of emphasize and optimize the quantum properties of interest. So this is, is the platform that we use it. We'll look at molecular beam epitaxy and angle resolved photoemission spectroscopy, and I'll get to those, what those mean in a minute. But in essence, we have all of these tools coupled together because both of these are very vacuum sensitive techniques. And the idea is we want to synthesize these materials and then interrogate the electronic structure of the materials in order to optimize the electronic structure to give us the properties that we desire. So molecular beam epitaxy, what is this? So molecular beam epitaxy is as complicated as boiling water. It is really just a vapor pressure effect. And so as you heat up water in a kettle, the vapor pressure changes. And so now you start to have a lot of, a lot of the water that kind of emanates from the surface. And as it gets hotter and hotter and hotter, you have more of the vapor that kind of emanates from the surface. And then you just have some little spout that directs it into a particular direction. That's it. This is really all of what molecular beam epitaxy is. The difference, though, is, of course, we are using different materials, different pure atomic materials that we can stick in these crucibles and in these diffusion cells. And these diffusion cells is just a crucible with a filament wound around it to get it hot. And then we just stick it inside the vacuum chamber. And you can see there's a lot of different materials that we can use this method to create a lot of different structures, a lot of different materials. And so now we can kind of pick and choose the atoms that we want in these materials and have them, generate a lot of these exotic materials. And so here, the basic idea is we have these atomic sources. We put them in the vacuum chamber. We heat up these atomic sources, and the materials start to effuse from these diffusion cells. And now we'll have a crystalline substrate, which kind of acts as a template that has the symmetry that we want our material to have. And so all of these materials will then impinge on this surface, and they'll hit the surface and they'll kind of rattle around. Some of them desorb, some of them move around, but then they'll start to chemically react with each other. And so this is how we form the chemical bonds, and this is how we can form new materials layer by layer. And now we can start customizing the materials that we want. We can customize heterostructures and interfaces that we want to start learning how to tune and control the material properties from the atoms up. And we will use a reflective high energy electron diffraction. This is sort of a scattering process where we can shine this incident electron beam on our surface. Now, these are thin film materials, and so it's a diffraction process, but, since we are looking at a surface, we don't look at it, we don't have, reciprocal lattice spots. We have this reciprocal lattice rod because we are breaking symmetry at the surface. But as this Ewald sphere, where it creates, or cuts through these rods, we can generate these streaks that will kind of tell us the symmetry and the crystalline quality and the type of material that we're looking at. And so we can look in these materials and looking at the read, it can kind of give us some insights into how they grow, whether it's going to grow layer by layer, or whether it starts to form these islands, or, if it starts to have sort of a step flow, process. And so looking at a lot of the structure in the read can kind of give us some insights into how these materials grow. And we can use that to better understand how to control the symmetries and the properties and the quality of the materials that we're trying to form. And so here, a lot of materials, if it grows kind of layer by layer, you can look at the intensity of these read patterns. And so now in a lot of situations, you can start to see oscillations as you start to form these materials layer by layer by layer. And so, here is sort of a lot of the oxides will grow in this mode. A lot of the calcinide materials that we're interested in, you can kind of see some of these read oscillations, but there is going to be a little bit of surface roughness as you start to grow the material. And so some of these oscillations will die out. And so there'll be a few unit cells of steps, but still overall globally, it's incredibly flat, incredibly uniform across the entire substrate. But here we can actually use this information to understand the structure and the properties. And here, this is the growth of strontium titanate, where we're actually controlling the individual sources of the material, and we can actually control the structure and get the structure to flip while it's growing. And so now we can find ways to control the symmetry, control the properties of the materials as it's growing. So that kind of gives you a sense of what it is or how we actually make the materials using molecular beam epitaxy. So how do we look at the electronic structure? And so looking at the electronic structure, we use angle resolved photoemission spectroscopy. And so ARPES is really nothing more than a fancy photoelectric effect. So most people know Einstein, is famous for relativity, but he actually won his Nobel Prize for the photoelectric effect. And in essence, what this is you have this energetic light that impinges on our sample. This light couples with the electrons and it gets them into an excited state. And so now if this excited state, if it has enough energy that can overcome this, the work function of the material, then that electron will fly out of the material into the vacuum. This is the photoelectric effect. And so what we do in ARPES is we shine the light on there, and as these electrons come out, then we have these hemispherical analyzers or time of flight of analyzer, where we actually measure the energy and the momentum of these electrons as it's coming out of the material. And so now using some very simple conservation rules, we can kind of understand how that electron was behaving inside the material. And so now we have these hemispherical analyzers. We can kind of look at the angle which defines the momentum of the electron, and then we can look at this hemispherical analyzer, the trajectory around this hemisphere, which will define the energy of the electron. And so here we can see one axis of momentum, one axis of energy, and then we can take our sample and rotate it to where we can access the other parallel momentum space. Yes, go ahead. It depends on who you ask. So I will kind of go and compare and contrast the differences to this, but it really takes all of the techniques to kind of understand how this thing works. And so I know there was a lot of investigation in looking at the STM aspect of it, and so I'm kind of giving you the other side. But I'll have a slide that kind of compares and contrasts the improvements and the differences between the two. So I'll come back to that question here in a minute. And so, by rotating the sample, we can access another momentum space. And so now we have a multi-dimensional data set that is looking at how the electrons behave inside the material. Now, of course, only the parallel momentums are conserved. And so, because we're breaking, we have a surface, the KZ component of the momentum is not conserved. But there are tricks we can do with the energy of the photons to kind of give us a sense, and a little bit of modeling to give us a sense of what that KZ momentum is as well. So we can map out the entire, KX, KYZ, and energy electronic structure of this material. So in essence, what we're doing is we're looking at the band structure. And so now we're looking at the electronic band structure. We're directly measuring the electronic band structure of the material. And so we can see that, with our analyzers, we're down to millivolt resolution. And so we can get a lot of exquisite details in how the electrons behave inside these materials, down with millivolt resolution, and we can go very deep down into the bands. But now to get back to your question about the comparison between what we can see in RPES and what we can see in STM. So, we can see in theory, we see these spaghetti plots where we're looking at the electronic structure. And so this is directly what we are probing in our RPES here. So this is a charged density wave material to where we're looking at different slices as we see how the electronic structure evolves, and we're directly probing it. But now in STM, you can actually do DIDV and look at the density of states. And so the difference between what we're seeing here in the density of states is the density of states is nothing more than integrating this along momentum. And so if you integrate this along momentum, you will get the density of states, which you can then compare with your STM or STS measurements. Now, another difference is the STM, it's a very localized. You're looking at a single atom. As you do a spectroscopic measurement, you're looking at the local density of states on that atom. To where here, our RPES beam spot is on the order of tens of microns. And so we're looking at a more average of the electronic structure over a macroscopic scale. And so these are some of the differences between STM and STS. But now one important thing to remember, though, is for RPES, it is related to the band structure, but we don't directly measure the band structure. So the difference, though, is here's the charged density wave material that I showed you before. And so now we have a situation, this is the normal state. When you go down into the charged density wave state, you have these multiple charged density waves that kind of reconstructs what this electronic structure should look like. And this is evidence of the Fermi surface, to where we kind of take our multi-dimensional data set and we just look at one energy in Kx and Ky at zero energy, and this is the Fermi surface. And so now one thing important to remember, though, is we don't actually measure the band structure, we're actually measuring the spectral weight. So in theory, we're not looking directly at the eigenvalues, but we're looking at the square magnitude of the eigenvectors. And so this is something that is important because you can see a lot of these weird intensity modulations and understand how it relates to our actual band structure. So what it is we actually measure. So this is what is our intensity proportional to. So in this formula, we have matrix elements, when I'll get to, we have our single particle spectral function. We have a Fermi direct cutoff because we can only measure the electronic states below the Fermi level. And then we have this instrument, resolution ellipsoid based on the energy and momentum resolution of our instrument. And so, measuring quasi-particles is what we're really looking at, because the spectral weight, you have the self-energy that's kind of wrapped into the spectral weight, but not only the band position, but the line width or lifetime. Because you can have real particles like electrons, but then you have all of this cloud of other particles around it that can kind of screen it and its interactions with all of the other, electrons and particles in the system. And so this is how we get this quasi-particle picture. And so now it will actually behave sort of like an electron, but it could have at a different mass or a lifetime based on all of these many-body interactions that you have that are happening inside that. And so this is what we directly measure with ARPES. We can see signatures of all of this evidence in there. And so we have the bare band that you can calculate with DFT. A lot of the electron-electron interactions could change the bandwidth. If you have electron-phonon interactions at the energy of the phonon, you can kind of see these kinks. And in ARPES, all of these, the bare band's electronic structure and all of these many-body interactions are actually encoded into that data. And so now we can start to understand the electron-electron interactions, the electron-phonon interactions, the electron-boson interactions in general through our data itself by looking at cuts along momentum and cuts along energy and how it compares with a lot of our models and our theory. So, hello, there we go. Matrix elements. Another unique thing about this is we can actually have orbital sensitivity to our electronic structure. And so if we have right here, you have this sort of D wave orbital here. And so, at the detector, the wave function has to be even or we won't see any intensity at the detector. And so now we have a mirror plane and there's sort of selection rules that are based on the vector potential of the light hitting the sample and, the momentum of the electron propagating away from the surface. And so by looking at this mirror plane, and if it's even or odd symmetry, based on this scattering plane here, we can set up these selection rules that can either enhance or suppress the intensity based on the symmetry of the orbital. And so now, here you can see that this has even symmetry. And so if we have, our a parallel here to this mirror plane, then we're going to enhance the intensity. But if you rotate the sample 45 degrees, then it would be odd symmetry and we would suppress that. And so then we would have to have a vector field perpendicular to that mirror plane in order to enhance that intensity. And so now we get some orbital selectivity to kind of understand the orbitals that are playing a role in a lot of the physics and the electronic properties that we see. And so in addition, we actually are able to measure the spins of the electrons coming out. And for our topological materials, this is really important. And so there's different ways of doing this. You can do it by Mott scattering or exchange scattering. But in essence, we have these detectors that can actually look at and measure the spin and quantify the spin of the electrons that are coming into our analyzer. And so now we can measure the energy, the momentum, the orbitals, and the spin component of these electrons using this technique. So we have a complete picture of what the electronic structure is, and then we can start to think about what that electronic structure means to the properties of interest in our quantum materials. And so here, we can, in essence, we can use these techniques to synthesize materials with very well-defined symmetries, with very well-defined interfaces, stack them together with all of these different, materials together. And now we can start to interrogate the electronic structure so that we can understand how to tune, control, design the emergent phenomena, the quantum properties of interest out of these materials. And so, for the sake of time, these last few slides I'll kind of run through kind of quickly, but I want to give you a sense of an example of how we deploy these techniques in, the Quantum Science Center for some of our materials of interest. And so one of the materials that we're really interested in is this compound of iron, tellurium, selenium. And so this compound, it is a member of the iron nictide superconducting family, which has, is similar to the cuprate superconductors, but, does have more complicated Fermi surfaces because the Fermi surfaces will change as you start duping and controlling the electron count. But, here, this iron, tellurium, selenium, it's the simplest of the structures, but, now we can take the selenium and start doping it with tellurium, and you can kind of see a lot of the behavior of the superconductivity in these materials. Now, here's where it gets interesting because as you start doping tellurium in for the selenium, you change that spin orbit coupling. And so at a certain doping, at about 50-50 doping, these PZ bands will get pulled below the Fermi level and you'll create this band inversion. And the band inversion from this, spin orbit coupling will create these topological states. You have these topological states, bulk boundary correspondence, you have this Dirac cone that will appear on the surface. But now we have an interesting situation where you have a trivial superconductor, but on the surface you have these topological surface states. And so this in itself is a candidate topological superconductor. Now, some of the complications here, though, are how we interrogate it and how do we confirm that this is indeed a topological superconductor. So in our ARPES, there are certain things that we would want to look for and we have to confirm to see if it's even a candidate topological superconductor. It has to have surface states. We have to see the spin momentum locking, and you need to see this S-wave gap in the topological states. But this is complementary to the STM, where in the STM you have to see these zero bias peaks because this is, again, sort of a half electron, half a hole. And so these Marana modes are going to be a quasi-particle that lives at zero energy. But there's going to be a lot of other trivial states that might appear inside this superconducting gap. And so you have to be able to discern those from a lot of these trivial states. But in the end, with all this evidence, it always comes down to a lot of convincing and arguing with the community whether this is really a Marana mode or not. And so these are local probes. There is no definitive evidence from these local probes that these are indeed Marana modes. And so in the end, we will have to do fusion and braiding in our devices to confirm the non-abelian statistics that we're after. But we can use these signatures to actually confirm that these are candidate platforms worth investigating and worth understanding. Now, one of the problems, though, with this material is, it has a lot of suggested evidence where if you put it in a vortex, and so if you have a vortex or put it in a magnetic field to create a vortex, you should generate the zero bias peak inside the vortex. And if you increase the magnetic field, have more vortices, you see fewer and fewer of these things indicative of the interaction of these Marana modes. And, there's also, other systems to where you can put just a monolayer of this on strontium titanate. And you can see on one end, you can kind of look what looks like a Marana mode. But areas where you see these sort of 1D features and the Marana modes are next to each other, they start to move off of zero energy, once again, indicative of interactions between these modes. But in the end, the challenge with this is a doped system. Ideally, it is going to be about a 50-50 doping. And it's just this inhomogeneity that is really making it tricky for us to understand and validate these systems. Because the variation of the chemical potential can create a lot of these trivial states that will kind of mask our ability to see the Marana mode or possibly interact with the Marana mode to disrupt the interesting quantum properties that we're looking for. And so one of the things that we're doing at Quantum Science Center is how can we sidestep this? We want systems that have the topology, we want systems with enhanced TC, but we want to be able to minimize the inhomogeneities from this doping. And so here, we're just lucky enough to where we can look at this iron selenium tellurium, but if you grow it on bismuth telluride, which is a topological insulator, you can do this and maintain a very, high transition temperature, but with less and less and less doping. Now, here's a situation where we're not really looking at the topology that is in the iron tellurium selenium because we have the topology that is in the bismuth telluride itself. And so here, the iron tellurium selenium is just a superconductor. And then we have the bismuth telluride, which is a topological insulator. And so this is a candidate Foucault model of topological superconductivity. The advantage here, though, is the fact that we can actually grow it with less and less doping, less and less selenium doping, so we can improve the homogeneity of the system itself. And so for the sake of time, I'll kind of just skip over this, but we do a lot of X-ray diffraction, a lot of transport properties to kind of confirm that these are indeed superconducting, highly crystalline materials. But here, it's more than just controlling the superconductivity. And so here we're starting to see some of our ARPES data where we can look at the topological insulator underneath, and then we can grow the thicker films and see the superconducting band structure of these materials. And, we can look at it in STM and see that as we start reducing the doping, of course, we're generating much more uniform films, much more, and so this uniformity will help us improve the size of the superconducting gap, and it'll help us, reduce any of these trivial states that might appear in the superconducting gap. But what's important is if we really zoom into the Fermi surface, here is sort of a thicker film, but as we zoom into just a single monolayer, because once again, ARPES is a very surface sensitive technique. It's the light comes in and the electron comes out, but the electron is highly charged, and so it's very light, and so it's very reactive to the things around it. So there is an escape depth to which we can, get the electron out without it interacting with something. And so here, we can kind of see, in the monolayer limit, we can actually see the superconducting states and these topological states. And we can see how the electronic structure changes as we change the doping of the material. Now, even down to the monolayer limit, we see that this thing is still superconducting. A single unit cell thick iron tellurium selenium film is still superconducting. Yes?
How is information stored in topological superconductor? How do I make slides?
I would assume that Chayden would actually cover a lot of that in his talk, and so I don't have any slides on those. But in essence, what you want to do though is if you have these topological superconductors in this Foucault model, where you have a 3D topological insulator with an S-wave superconductor, the question is how can you actually get the information out of that? How can you actually use this for quantum computation efforts? And so I just deleted all my backup slides. I had them there. I should have showed those. But, so now if you put it in a magnetic field and create these vortices, you'll have these Marana modes that can appear at the center of these vortices. In essence, though, these are non-local states. These are non-local entities here. And so now if you have a pair of vortices, they know where each other is. And so now the question is, as you start to move one vortice around the other, you start to entangle them. And so now there is going to be a memory of the motion here because these are non-local states. And so if you take these and start moving them around each other, you get them entangled with each other. So now if you have these multiple vortices, the way that you entangle it and how you entangle it, these motions, if they commute, then you could form trivial states. But if these motions around each other don't commute, you'll form these non-abelian states. And so this is an essence of how you take these Marana modes that are on the surfaces of these topological superconductors and actually encode a lot of the information to do the braiding and fusion operation. And so, yes. Yes. So in essence, this is what we look for, and this is how we do it, because we can take these, you have two states, they will form a qubit. If you move them together, you can generate a fermion parity. As these things annihilate each other, you'll be either left with electron or left with just vacuum. And so this is the two states that you want to have. But of course, as they separate from each other, then you have this entanglement and you have a sort of a superposition because you can't tell where the Fermi parity is a priori. And so as you have these multiple qubits or these multiple states that start moving around each other, you can create these braiding operations. And this is how you get the quantum information encoded into these things to do the quantum computational efforts. And so with that, so I'll just go ahead and finish up here real quick. One of the important things here is to make sure that we have the spin momentum locking at that interface. These are these interfacial states, and we've been able to confirm that. There is a very rich rabbit hole for how you tune and control these things that I'll just skip over through. But of course, in the end, these are local probes, and we have to start thinking about how can we use non-local probes to truly understand and distinguish between these Marana modes and a lot of these other trivial states that might appear within the gap. And so also within the Quantum Science Center, we're trying to learn to develop a lot of these non-local techniques to try to confirm and develop contrast between what is a Marana mode and what is not a Marana mode. And of course, a lot of the devices and everything that we need to develop, these are things that I'm sure Steve and Jesse and others have actually been able to cover in a lot of their aspects. But I wanted to give you a sense of just how we make the materials and how we interrogate the materials to optimize the properties to generate these potential platforms for topological superconductivity that we can then start thinking about how to fabricate devices out of and how to actually generate a lot of our qubits in properties in interest. And so with that, I'll be happy to answer any other questions. Thank you.